Okay, guys, so it's me again. So this time I'm going to be presenting the work on the Signal Integrity Work Group, and I'll make a start straight away. So this is, before I begin, I need to make a shout out to my co-lead, who's Kai Wang from Intel. He's an expert in signal integrity. I am not. I'm more of a fluids and thermal guy, as you know, probably from meeting me before. So I'm on my learning curve, but my role is to really coordinate the group, and Kai's here to make sure that we have the technical level and the technical challenge in the sessions, and he certainly does a fantastic job of doing that. And I really want to credit him for the majority of the work in the leadership of the technical content. As you know, probably from your experience in immersion cooling, is that the vast majority of servers are not born destined to go into an immersion tank. The majority of them are designed for an air-cooled environment, although we are seeing some changes to that. So why do I reference that? Well, the reason for this is that the environment that you immerse a server in, if it's not air, then the information that flows through that server, the electromagnetic fields that are necessary to pass signals and power through the conductors, they sense this. It has a feedback. It has an effect. And this becomes more and more apparent as we have higher data rates and a greater range of equipment in the immersed environment. So as you probably know, as electrical signals travel along transmission lines or conductors, you don't have the transmission of information directly on those lines. It's a field around that line which is generated that causes the information to flow. And those fields, as you can see in the image on the top right, they interact and are impeded in part by the material that is on the top and bottom side. As you can see here, we have a solid dielectric underneath the conduction, the transmission line. On the top, we would have air. If you replace the material on the top of the transmission line with a liquid, it's going to store and dissipate energy and slow down, distort, reflect, and delay the information. And in the image, you can see along the horizontal axis a time trace of information passing along a transmission line that has multiple components, and you can discern the change in the impedance, the resistance to the transmission of that information as the signal passes in between different types of equipment that are in air, in blue, and immersed in liquid, in red. Some of them have a small change, and some of them have a large impact. And it's the large impact items that are going to spoil the party for immersion. Strangely enough, sometimes you get a reduction in impedance that sounds like it's an improvement in performance, but any change to the signal causes things to go out of skew in the timing of the reception of the information. So it's not a case of it's faster in immersion, which may be the case, but just because it's different, it means you've got to retime, and that's where the problem comes from. So how do we control this? Well, you need to know what the fluid properties are, which impacts on signal integrity. You need to know what the types of equipment are, which are carrying the signals and the data. And you need to know what kind of methods we have available to quantify the effects, and what can we do about it. That's probably the most important point. Something that people do already in the design of PCBs, for example, is introduce these features in design. You see the red diagram at the bottom. You can see that there's some straight transmission lines and some that have some wiggles in there. Why do they have wiggles? That's more copper, that's more cost. Well, that's an attempt to extend the length of the transmission line to retime in the hardware the arrival of the signals. You can do this as well in software, but you can only do it once, essentially in hardware, and it's a multi-million-dollar project to have the validation or the certification of equipment. And to do that again for immersion is not economically viable at this point in the adoption of our technology. So remaking the design and recertifying isn't an option, so we need ways that we can fix things later on. The properties of the immersion fluid which are most critical for signal integrity are shown here, the dielectric constant and the loss tangent. Dielectric constant has a value of 1 for air, and for typical fluids it's around 2, and so there's a doubling of the dielectric constant. Doesn't mean to say you have a factor 2 change in the electromagnetic performance, but it does have an impact. Within OCP, we've set a base specification, which has been let out again by Intel, to have a dielectric constant less than 2.3. If you stay below this value, then the impact of the immersion of your equipment in a liquid is going to have a minor effect. It may still put things out of the certifiable ranges, but we're trying to control it here by just controlling the fluid properties. The loss tangent does become a major effect at higher frequencies, and when we get into the gigahertz range, then loss tangent does become important. Again, the value for air is 0. We have a finite number for liquids. And again, the OCP base specification to control this, the impact of this for high data rates is less than 0.05. The 2 fluids that you can see as an example, of which there are many, are well within that range. So that's a good thing. So we can control the liquid by having a specification, and when we select a liquid for a certain purpose, we can use the base specification from OCP to increase our chances of success. When we get into immersion, though, you need to, of course, do a component-by-component test to understand if you have an issue, what you can do about it, where you're going to focus your attention. Within the community, which we've had over 1 year's work, we have had many examples of equipment vendors showing their testing data for immersed connectors, cables, PCBs, DIMM modules, all kinds of things, and it's a really rich set of data that we have. And through that, we're developing methods for testing, for immersion equipment, and methods of reporting. So on the left-hand side, you can see the scope of the documentation that we are trying to converge on, how we ask people to share and record data on their testing. And we're also looking to compile a library of tests that have been contributed so people can take a look at that and make their own assessments and guide their own testing in their own areas. An example of the data you can see here. So this is on the bar charts. You can see the eye margins between air testing in blue, and for short-term and long-term up to 1 year in gray for immersion for a DDR5 module. And you can see that there is a very slight effect, but not a significant degradation of performance in immersion, which is great news. So this is data coming from Intel, and this is for the memory modules. We also have data in the table. You can see the first data for the DDR modules on the top line. You can also see for other equipment, like for PCIe Ethernet and for optical Ethernet, we have past conditions achieved in immersion. However, we do know that in some examples of equipment, then there is less good news to share on the impact of immersion. One of the areas where we know that we have some challenges, is for where you have an exposed microstrip. That's the most basic example, where you have a copper transmission line that has solid dielectric on one side and liquid on the other, and where you have a connector which has very high frequency, high gigahertz frequency data communications. So what we're doing in that case, while we have the testing data occurring, we're also using simulation. We chose the microstrip because it's basic and where people can test their assumptions about how the physics works and to validate the methodologies in simulation. And then we picked something that's more complex, a connector and cable, which is XMAX 2, that's very relevant in the industry right now. The reason that we picked that one in particular is because it aligns with the OpenAI build spec for the universal baseboard and the QSFP cable connector between them. And this is one component of many along the signal path that you can see shown by the black line that we're going to gradually and sequentially simulate the signal integrity performance of these components, and in doing so, showcase the methods of mitigation available to us in immersion. So this is the first of many simulation case studies that we're going to do, and you can see at the top of the screen there's an impedance budget for this single signal path, and the challenge is, can we get back to 30 decibels when we go from air to liquid? Which components in this signal path are reducing the impedance, and how do we add the impedance back in? And maybe it's a different cable, guys, or maybe it's something else. Okay, that's enough of a spoiler, I think. Okay, so takeaways. So as you can probably tell, it's best to avoid issues. So in design, avoiding the exposed conductors, like that strip line that we showed you before. So embedding things within solid dielectrics is really doing a great job of avoiding the issue of immersion. Designing things with consideration for the properties, and you saw the Intel base spec for the fluids, so considering those in your design processes for components is also a good avoidance strategy. Increasing the signal to noise ratio, of course, it's fundamental, is going to increase your chances. And also using on-chip methods to avoid having to fix things later in the design process, is also going to improve your chances. Finally, a consideration that we're looking at the moment, and it's a little bit unclear, but we're working on this, is that in some cases the dielectric properties will vary with temperature, but also the quality of the contact between the connector bodies also varies with temperature due to expansion of materials. So there is a thermal effect, which is secondary. Right now it's out of scope from the work in the group, but we need things to be realistic, so we're trying to consider the other failure modes. There we go, we did connect it across to failure modes, which may occur in applications. So we're keeping it simple as far as we can, using real examples of equipment as far as we can, but also considering the different failure modes which may occur in the immersion environment. Okay, guys, that's it for me today. Only to finish by saying that we have an open group. Please do join it if you can. We'd love to hear from other equipment vendors with their equipment to test. If you want just to know how people are doing their tests, so you can do your own, or indeed your own simulations, then we're very open and can share ways of working with you. So it's the first and third Monday of every month, and the QR code's on the screen for you to sign up. Thank you very much.